Ever pondered if time travel could be a reality, not just a figment of science fiction? Our fascination with time travel is not new. Since the dawn of storytelling, we've been captivated by the idea of journeying through time, altering the course of events, or catching a glimpse of the future. But what if I told you that time travel, in a sense, is not just a product of our imagination? What if I told you it's a scientifically accepted phenomenon? This is where we cross the threshold from fiction into reality, with the concept of time dilation. In the realm of physics, time dilation is a direct result of Einstein's theory of relativity. It's the idea that time moves differently depending on your speed and gravity. It's the bridge between our dreams of time travel and the cold, hard facts of science. But what exactly is this elusive time dilation? Let's delve deeper. Time dilation, in simplest terms, is the difference in elapsed time as measured by two observers. It's a concept that seems to leap straight out of the pages of a science fiction novel, but in reality, it's a fundamental part of our universe, grounded in the foundations of Albert Einstein's theory of relativity. Let's imagine a scenario. Picture a train hurtling along the tracks at an incredible speed, close to the speed of light. On this train, there's a passenger observing a bouncing ball. To this passenger, the ball simply moves up and down, but to an observer standing still on a platform, the ball's path isn't just up and down. It's diagonal, tracing a longer path because the train, and everything inside it, is moving. Now here's where time dilation comes into play. If we think of light as the ball in our example, the light inside the moving train has to travel a greater distance than the light observed from the platform. But the speed of light is constant. So for the light to cover this extra distance at the same speed, time itself has to slow down on the train. That's right. Time slows down when you're moving incredibly fast. That's time dilation for you. But speed isn't the only factor that influences time dilation. Gravity plays its part too. You see, according to Einstein's general theory of relativity, gravity is the curvature of space-time caused by mass. So a massive object, like a planet or a star, can warp the fabric of space-time and slow down time. This is why time runs slower the closer you are to a massive object. It's also why your head ages faster than your feet. Time dilation is an intriguing concept that challenges our everyday perception of time. It's not just about ticking clocks and changing calendars, it's about the fabric of the universe itself, the dance of light and gravity, and the incredible speeds at which we move. Now that we have a basic understanding of time dilation, how does it influence our notion of time travel? Time dilation is the closest thing we have to actual time travel. But how? Well, let's imagine you're an intrepid space explorer sailing through the cosmos at speeds approaching the speed of light. According to Einstein's theory of relativity, as you move faster, time for you would slow down relative to someone stationary back on Earth. In essence, you'd be living in a world where each tick of the clock is a mere whisper in the roar of the universe. This concept has been explored in numerous science fiction scenarios. Remember the blockbuster movie where astronauts return from a journey to find everyone they knew has aged significantly while they've barely aged at all? That's time dilation at work. But it's not just a plot device for Hollywood. It's a scientifically proven principle that could, theoretically, allow us to travel into the future. But before we start packing for a time-traveling space journey, let's consider the challenges. As fascinating as time dilation and time travel might be, they come with their own set of challenges. Achieving near-light speeds isn't a walk in the park. It's a Herculean task that takes a colossal amount of energy. We're talking about an amount that far surpasses anything we currently have at our disposal, and even if we conquered this Everest of energy requirements, we'd still have to navigate the paradoxes associated with time travel. Confronting these paradoxes challenges our understanding of cause and effect. Imagine visiting the past and accidentally altering an event. You've just created a paradox. Did the original event ever happen? Or has a new timeline sprouted from your actions? It's a loop that can make your head spin faster than a pulsar. Despite these challenges, the concept of time dilation and its implications continue to captivate us, pushing the boundaries of our understanding of the universe.